trying to do a really quick review for you of all the topics, really quick. Okay, this will be posted later today. This is Sunday morning. First of all, you do have to know nomenclature. I'm not going over nomenclature here. You've had lots of sheets with nomenclature. You have lots of things to learn. You really have to learn the benzene structures, particularly the bicyclos. You should be able to work with a basic benzene. So for example, if I give you, something like this, and it's got, that on it, you should be able to say that is 1-ethyl-3-methyl-benzene. You should be able to do something like that. I don't expect you to know all those special names like benzaldehyde, benzoic acid. I wish I could put that in, but we just didn't do it. But you are responsible for all the bicyclos, the ones with nitrogens, like I showed you in class, and the polycyclics. Okay, that's important. As far as the Diels-Alder goes, in my review in class on Friday, I did a lot with the Diels-Alder. I'm also posting the answers to that review sheet. I will reiterate, one of the things I noticed is that people were not aware that the stereochemistry of the diene translates into the product, and the stereochemistry of the dienophile translates into the product. Okay, so for example, if you have this structure, okay, and you're doing a Diels-Alder, I tried to address some of these issues. Let's make it like that. These groups are going to be in opposite direction, okay, in the resulting products. A lot of you really have to get into using numbers. If you don't use numbers, you're going to have trouble with this, right? So this is 1, 2, 3, 4, 5, 6. Now, why did I put them in opposite directions? I put them in opposite directions because this is an inner group and this is an outer group. They are cis on the new ring if they're both outer or they're both inner. Okay? I just noticed people didn't really pick up on that. I covered that in lab lecture. Okay? So you should have really good notes on that. And also in your packet, there's a little series of notes on the Diels-Alder, where I talk about dienes, good dienes, bad dienes, good dienophiles, bad dienophiles. Also, this kind of got emphasized. I'm in a rather precarious situation here today because I do not have my correct support for this. I usually put it on my easel. My easel's broken. Okay. The other thing that you should be aware of is that, there are other bad dienes. I will reiterate from class, you are allowed to rotate these around. A lot of people aren't aware of that. Then when you rotate them, if both groups end up in inner positions, you have to keep track of where they are. And you might say, well, how do I keep track of where they are? Like say that's what we were given as our problem. And it's supposed to react with, like, say, this compound. Okay? Remember, triple bonds can react. I'll put a carbonyl on there. When you rotate this around, you look at this and you would say, oh, this is a Z double bond and this is an E double bond. Okay? So when this rotates around, this would be like this. And this would be E. So this would be inner outer. This, triple bonds, have no stereochemistry. And by the way, I was writing out places where you don't have exo and endo. And one place you don't have exo and endo is when you have a triple bond. I was trying to think of the fifth scenario. Remember I said it was like baseball. In baseball, there are 5 ways you can get on base without getting a hit. Don't worry, I'm not going to ask that on the test. I should, but I'm not going to. So we get this. Remember this. This I don't write well when I'm bending over, okay? But these would be trans to each other. But there are other bad dienes. So had I put this group here, and notice also the double bond, you don't put wedges and hashes on that carbonyl. We've talked about that. Okay, this is still all Diels-Alder, but I think that's where people have the most trouble. Okay, if this group had been ZZ, this would be a bad diene. When you rotate it around, there's too much steric hindrance there, and it can't achieve the S-cis conformation. So all dienes have to be able to achieve the S-cis conformation. I just want to reiterate that. So what are the 5 times you don't have exoendo? You don't have it here, okay? You don't have exoendo when you have a triple bond as your dienophile. You don't have exoendo when the diene has no substituents on it. So if this had no substituents on it, you would not have exoendo. You also have no exoendo if the dienophile has no substituents on it. They don't have to both be that, one or the other. Okay? You also don't have exoendo, at least that you can evaluate if you have a trans diene. And remember, the stereochemistry of the diene translates into the product, and the stereochemistry of the dienophile. But I went over that. Okay? And that's also on the sheets. Okay? One of the things, I'm doing this because some people miss the review on Friday, and I can't, make up for all of that, unfortunately. But, we were doing very hard Diels-Alders. So, if you had to synthesize, for example, this kind of a product, I think this is kind of an interesting problem. So say you had to synthesize like this. Remember, good dienes, dienophiles rather, have electron withdrawing groups on them. And you have to be able to ascertain the difference between electron withdrawing groups and electron donating groups, and I'm going to get into that. Okay? So if you were doing this and you're saying you have to synthesize this. Okay, I'll just write that up here. You have to synthesize it. All right, you would use your numbers. Make sure you're using your numbers. 1, 2, 3, 4, 5, 6. Why did I choose those numbers? I chose those numbers because the double bond normally ends up between 2 and 3. Now, had I used a triple bond as the dienophile, I'd have 2 double bonds, and the double bond with the electron withdrawing group would be the 5, 6. Okay? So then when you go backwards, I always tell people to draw any old, just the most mundane Diels-Alder and number it. So going backwards, the numbers work just as well as going forward. Okay? So then you say to yourself, oh, on 1, I would have a methyl group, and on 4, I'd have a methyl group. And what this is telling you is that the methyl groups are in the same relative position. It's either ZZ or ZE. Okay? And then you'd say, oh, these are cis, so these must be cis on the dienophile. So that's all good. That all looks well and good. But the question is this exo or endo, right? So here's the problem that I was suggesting to you last week, was that there are some of these that you can't do. You just can't do them. Because if these are in the outer position, that means the inner position is H. So we assume when we do a Diels-Alder that we're going to get the endo. The endo, as I wrote on the sheet, is when the inner position, this is how I define it. Some people define it the opposite way. Some people define it as when the outer position is in the same direction as the substituent or substituents on the dienophile. Okay? But I define it as the inner position because a lot of times those are bridges. The inner position being opposite to the substituents on the dienophile. So if I reacted these two together, right, would I get this? Yes, I would get this because the H's, right, the H's are going in the opposite direction to those groups. So that's a perfectly legit endo. However, realize that the other isomer could not be made this way. So in other words, if I wanted to make this compound, okay? Unless I had some methodology to do it, make an exo, you can't make that from starting materials because, here's the point, you would have to start, and I'm just, again, emphasizing this idea about what exo and endo means. If you wanted to make that, you would have to have, right, the hydrogen, the hydrogen would have to go the opposite way, I'm sorry, the inner position, let's put it this way, would have to go the opposite way to those groups. And you're saying, well, that looks perfectly fine and dandy because you've put the methyl groups on the inner position and they're going opposite to those groups. That's fantastic. That looks great. But you'd say, no, I can't do that because that's not a possible diene because this diene would really exist like that. I'm sorry, like this. It just wouldn't rotate into that position because it's a bad diene. I wanted to emphasize that because I feel like a lot of times you can't look at a product and just go, oh, that's exo. It's just not obvious. You have to actually kind of write it out. All right. All right. So the next thing I wanted to talk about. Sorry about Anna Karenina here dropping off the thing. William Shakespeare took a dive to the floor there. I will get my easel, my painting easel is what I use for this. Okay, so what else do I want to talk to you about? Well, remember, you also have to be able to do ortho para kind of like justification, okay? So for example, if I gave you something like this, and I said, this is going to react with like this. All right, and no one should be horrified by that, and they should go, "Oh, it's a Diels-Alder, no problem." And you'd put your numbers in. And this will be my last Diels-Alder. I know I've done a lot of Diels-Alder, but I want to make sure people know the resonance aspects of this. Okay, so my first product would look like this if I kept it the way it's drawn. And then I'd have this as my product. Now this is the so-called meta product, okay? Now what we said in class was that the ortho or para, you don't get both, will usually win out over the meta, okay? So this would be your minor product, and you'd say, no, I really get more of the one with it flipped around. So I would get more of this. And you might say, why, Dr. Nerz, did you spend so much time on the Diels-Alder? We already had some Diels-Alder. The Diels-Alder is an amazing reaction. There is so much going on with the Diels-Alder reaction in terms of just theory and things that are going on. So you would actually get that product predominantly. Now what I expect you to be able to do is to distinguish between a donating and a withdrawing group. So in this case, this is donating because it has lone pairs right next to the pi system. It has allylic lone pairs, which we spent a lot of time talking about with acids and bases. And mind you, you need to be able to do acids and bases. I'm going to talk about reactions in a minute. Okay? So if you have this one, what you would do is you'd say, well, my resonance form that would be important would be, I would take this pair in and this pair out. Okay? And in doing so, okay, I would get a little negative charge down on that end carbon. And that's the theory that a lot of people use to explain the lineup of these things. Okay? Now this piece, this is an electron withdrawing group. Now how do I define them? Remember I said this is like the electron density through the pi system is moving that way, through the sigma it's moving that way. Electronegativity or polar effects really only define sigma bonds, okay? In this case, there's no resonance. Like if you took these pi electrons and started moving them in, you would generate a full positive charge on nitrogen, and that would be very unstable. What I told you was electron withdrawing groups are groups where the carbon attached to the pi bond is delta plus, okay, and has no lone pairs that you can use as a lone pairs. That means the electron density goes the other way. I wanted to just reiterate this because this is important. Now these resonance forms look really weird. They're not the happiest things to work with, okay? But what this shows when I do this is that this negative end is down here on the bottom, and this positive end is up on that end. And this is one of the reasons electron withdrawing groups are kind of useful, okay? So this would prefer to line up in such a way, and you know, we know a lot of chemistry is positive, or at least we can rationalize a lot of chemistry as positive and negative. That's not the best bond angles there, but what I'm saying is it's going to line up so the plus and negative get together. And that's why we like to have, you know, a donating group on one piece and a withdrawing group on the other piece. That makes them more attracted to each other, and it also helps them line up properly. So that's why that product dominates, because that lineup is a better lineup from a charge distribution. This is very closely related to this business about NMR. You know, and I think one of the really, here's a really interesting problem, right, is flutamide. Now, what's the deal with flutamide? Flutamide's kind of funny. I don't know. Well, let's say we get something like this, for example. I gave you one on the sheet that was kind of ambiguous, and I really didn't mean for it to be so ambiguous. This kind of relates to what you did in lab, because it's kind of like flutamide. It's kind of like the amine you used in flutamide. So I was telling you this thing about NMR, and it totally relates to the thing I just did. And the reason I did it is I wanted you to see how electron donation and electron withdrawal also like just extends into NMR spectroscopy. So what kind of group is this? You would say this group is an electron donating group, okay? So, and you'd say, why? Because this lone pair is allylic to this system, okay? So this would come in, come out, right? And I expect you to be able to draw resonance forms like there's no tomorrow. And I'm assuming you do know how to do this because you seem pretty good at it, all right? So if you took this, you could take this all the way around this benzene ring, and you would find that the negative charge, that this group, kind of similar to my Diels-Alder case, this group puts negative charge at the ortho and para positions. Now, this has implications in chemistry, and particularly last semester when you were doing aromatic chemistry. But in NMR, what it does is it puts a certain amount of negative charge at the ortho and para positions. And you should start looking at this in your NMRs in the lab, because you would see like this hydrogen, these hydrogens, this one, maybe this one, maybe particularly this one and this one. These would be at lower than normal ppm. Okay? Now, why is that? That's because those hydrogens have more electron density around them. Is everything okay? Mm-hmm. They have more electron density around them. Electron density usually creates a field in the vicinity of the hydrogen that opposes the external field. And I kind of drew some pictures of this on the worksheet. But the idea is if I have an H and it's on a carbon, generally speaking, when you take the sigma electrons and you put them in this superconductor, the electrons start rotating. And they rotate in such a way that the hydrogen is sitting right smack in the middle of the donut. And I described that donut in class. And the donut opposes the main field. That's how magnetic fields work, induced fields. Okay, and it just happens to be sitting there. And then if you have resonance such that there's more density there, that little field actually gets bigger. So that means, right, the net field is the vector addition of those two fields. So that means when you've got a lot of electron density, what happens is you have a lower net field. And you can look this up. Like if you go into that database we have and you look up compounds that have donating groups on them, you'll see the ortho positions, the ortho and para positions are like at about 6.5 ppm or something like that. And that's because the net field has become lower, what we call B prime is smaller, right? And the equation is delta equals mu over 2 pi B. So if this has become smaller, this has become smaller, and this is proportional to ppm. You should also be able to work with electron withdrawing groups. A nitro group is an electron withdrawing group, and did I once again give you something that's counterproductive here? I didn't want to. Let's see what I did. Yeah, I guess I did. I want to put it somewhere where it's not so problematic. Well, let me just give you one example where it's not going to be counterproductive. Sometimes you'll find, like the one I did on the sheet, that they kind of work at odds with each other, and when they work at odds with each other, you kind of get kind of a balanced effect. Realize a group like this and a group like this has its biggest effect locally because it also has a polar effect. But just to show you a place where this nitro group would bring the ppm up. These tend to bring the ppm up. Okay. I have so much marker on me that it's not even coming off anymore. Okay, so if I have this is defined as an electron withdrawing group because it has no lone pairs on that nitrogen, and it has a delta plus or a plus. So in this case, I'd move the electrons this way out. That would make this carbon positive. And it would also make this a little positive and this a little positive. So you'd see they kind of counterbalance each other. But they don't counterbalance each other there, I don't think. Maybe they do. I think these are going to counterbalance. This is bugging me a little bit. But anyway, but let's just take this off for now, because that's kind of distracting. Let's say we have this. If I do this, if I bring this out, I just want to make them simpler so they're not so confusing. But if you go like this, right, what's going to happen ultimately, if you do all the work, is you're going to have a delta plus here, a delta plus here, and a delta plus here. You know, if you drew a hybrid. And you should be getting to a point where you can draw some hybrids. But the point is, this is the opposite effect, right? What's going to happen here is there's going to be low amounts on the low electron density at the vicinity of the hydrogen. That means this vector is going to be smaller. Because what happens is when there's a lot of positive charge, there's just a less electron density, there's less of a field. If this is smaller, the net vector is bigger. If the net vector is bigger, right, if that goes up, then the delta goes up. And if the delta goes up, that means the ppm goes up. So generally speaking, you're going to see that hydrogens that are ortho and or para to an electron withdrawing group are going to be like at around 8 parts per million, and hydrogens that are around, hydrogens that are ortho or para to kind of traditional donating groups are going to be kind of lower. They'll be like 6-ish. And sometimes when they're like working at odds with each other, you just end up at your plain old 7. 7's kind of the normal place, like on a benzene ring. But I want you to be able to use resonance to prove that. Okay, so let's talk a little bit about the reactions. Okay, and what I'm going to do is I'm going to do some things backwards. I always say students, there goes Anna Karenina again. So, students, sorry about the bug, I am really sorry about it. Let's try Shakespeare again. Maybe Shakespeare can hold this up. It's a heavier tune. Can you get that? Get the Shakespeare one, just the Shakespeare. That one falls off of easy. Maybe Henry could come and hold it up.
That's
that would
right.
be good.
There we go.
Henry would be entertaining at least. Reactions. All right, so you have reactions you have to know. One thing I brought up in class, which I think is important to realize, is there is stereochemistry associated with going from an sp2 carbon to an sp3. It's not particularly important in hydrates or in acetals or ketals because typically they're done symmetrically. However, in the reaction with the cyanide, which we did very quickly, okay, there is stereochemistry. So if you have, for example, some, ketone like this, and you add hydrogen cyanide. I did this in class, but I want to reiterate this because I feel like we didn't really talk about the stereochemistry. If you add these, and remember the pH has to be equal to 9. I hope you can work the Henderson-Hasselbalch equation, right? pH. Remember, we talked about this. I'm going to keep talking about it. I love it. It's really important. It was log A minus over HA. If you work through this, for this particular case, the pKa of hydrogen cyanide is 9. So 9 equals 9. That means the concentration of A minus and HA in this particular reaction are identical. So you virtually have 50% cyanide and 50% HCN. Again, the beauty of this equation is it tells you how much of each thing you have. All right, so this, we said, we do this sort of from a basic perspective. That was my approach to teaching the material. I was going from an acidic to a basic perspective. Realize that this cyanide has a 50% chance of coming in from the front and a 50% chance of coming in from the back. If it comes in from the front, it's going to push the O back. If it comes in from the back, it's going to push the O to the front, and that's going to create a pair of enantiomers. So, for example, if it comes in from the front, it would be like this. The O minus would be going from the back, and then you'd want to draw the protonation of this, okay? And I would get, and honestly, the structures of these things just aren't really complicated because, I mean, they could be, but you really are doing all the chemistry on the functional group. So you get this, but realize you would also get its mirror image. I wanted to bring that up because I don't think we talked about the stereochemistry of it in class. Okay, now the other thing I was going to show you, I can't do everything, I've done a lot of what we've done in class. But realize you're still responsible to be able to handle an acid-base equation. And the acid-base equations are going to be jumbled in with the Diels-Alder and with the newer material, which are these reactions of carbonyls. I think people are doing pretty well, but just be aware of that, okay? You have to kind of be able to distinguish things. I did send you a list of flashcard problems to focus on. That should be helpful. I've noticed in my office the things people are having the most trouble with are going backwards. So let's say I go backwards. Like supposing I've got, let's do two things backwards and then I'll stop. So supposing I've got this. One mistake people make frequently, so going backwards with this, you would add H3O plus, and you kind of like heat it up. The ocean would be water, okay? First event, when you're in acid, normally the first event is protonation, okay? So you would take your acid. By the way, it could be written that way. It doesn't necessarily have to be written as sulfuric acid, although I'll frequently do that. Or I might write HCl in water, I could do that. Okay, if I do this, I get an H like this. I'm warning you, I'm very fussy about resonance. Okay, so my next structure would look like this. I do apologize for the board situation here. I would get this, there's a plus charge there. This is the opposite of putting the acetal, or this is a ketal actually. The opposite of putting a ketal on is taking the ketal off. It's done by flooding the system with water so that the uptake of water is more important than the uptake of alcohol. When you want to put it on, you flood it with alcohol, and there's very little water around, but there is water around. So I'm very fussy about resonance, as you will see. I will be picky about it. I think you've already noticed it on quizzes. You said, oh, I didn't draw the resonance structures for the starting material. Like if it says to draw resonance structures, draw them. Now again, the reason I said stereochemistry is not usually an issue with these things is you're frequently putting on a symmetrical acetal or ketal. Okay, so you've got this plus charge. Okay, now what do you do next? The next thing you do, what you've done here is you've made this into a leaving group, so it comes off, and then you're looking at this and you're saying, hey, this is now a positive charge. It's a reasonable positive charge. It has some resonance. Remember, a mechanism is a story. This is flooded with water, so what's going to happen next is the water is going to come in. And honestly, when you can do the backwards, you really get them. Okay, so now we've got a water attached. The water will become the carbonyl. And if you draw your resonance, you'll figure that out. Next, you would want to do a proton exchange. Okay, so you'd want to do OH. I told you I gave you the power proton exchange, which means you don't have to draw them out. But remember, they're mediated by the solvent. Okay? Now, all this means is that this is going to make this into a good leaving group. That pops off. Look how nice and neat and clean this is. All right, now I've got an OH here. There's a plus charge there. This has come off and it's free. And remember, when these go on, they go on beautifully because the second reaction, remember these like theoretical things we went over in class? It's intermolecular. And intermolecular reactions are very favored from an entropic standpoint because you tend to go from one molecule to one molecule instead of from two molecules to one molecule. Systems tend toward disorder. If you looked around my house right now, you'd understand what I mean by that. Right, look at my office. Ha ha ha. So two molecules coming together and making one creates more order in a system. But if one molecule becomes one molecule because the process is intermolecular, that tends to maintain at least the same level of disorder. Okay? So I've got this plus charge here. This is creating disorder because it's falling apart. All right, now this has a plus charge, so there's another resonance form. And I always feel like if you're a meticulous resonance person, you always find the product. Because suddenly you'd say, oh, my goodness, that looks like a carbonyl. You would use a water molecule, because that's the ocean, to take the proton off, and then you have your nice ketone back. You're going to see later in the course that we're going to, very, very soon, we're going to use this as what's called a protecting group. Protecting groups are groups that you can put on and take off at will and under different conditions. Okay, now, last thing I'm going to do. I want you to realize, I'm not going to do a lot of synthesis because the synthesis of this test is going to be very easy. Unless it's Diels-Alder, I suppose, but it's going to be pretty easy. You know, we just don't have a lot of reactions yet. But realize, again, they're going to be all mixed together. The reactions are going to be mixed together. That's why it's good to take your flashcards and even make more flashcards and mix them up, okay? But just as an exercise, I was going to take an imine and go backwards. This is kind of an odd thing to do, to be honest with you. Like, so there's an imine. Like, so say I had the imine and I was going backwards. In principle, I could take this off with acid, all right? It's always a good test if you can go backwards, right? If you can go backwards in a reaction. So the imine, I said, was a lot like the formation of an acetal. That's why I did it when I did it. So I would start by protonating this. This is not something we do normally, but it can happen. You can hydrolyze it up. So say I do that, right? So now that's a plus charge. I just want to show you that imines are a lot like carbonyls, okay? So if I do that, then I would draw another resonance form. This is called one-bond resonance, or what I call one-bond resonance. Don't ask me why I used another six-membered ring. I just did. Okay, so now this is starting to come off. I don't know, N3. Okay. So now that's got a plus charge. So you'd say, well, what would happen? Well, if water was my ocean, the water would come in here, okay? And if you look at my mechanism I gave in class for going forward to make imines, you'll say, oh, I get it. You know, it's really just the same mechanism. She's using the principle of microscopic reversibility again. All right, so now I would do a proton transfer. This would become, and I want to say something about things I do on the board. Sometimes on the board I might leave like I left my hydrogens out here. You go by your notes, right? I give very good notes in class, or I try to anyway. All right, so now this is an OH. Believe it or not, that makes the nitrogen into a good leaving group. So I didn't put the minus H plus plus H plus. Sometimes people call me out and they'll say, in your video, you didn't do that. Your notes are kind of like and your textbook are your like rocks. But the notes, I actually give more detail on mechanism in class than textbooks usually do. Okay, so I'm popping that off. It's a good leaving group now. Why? Because it's positively charged, and when it leaves with its lone pair, it'll be neutral. I freed the amine back up, and now what do I have? I'm not saying this would necessarily be so easy, but you can do it. Now I've got the plus, right? This comes in, and you're like, lo and behold, there's my carbonyl again, because this is another group made from a carbonyl. Because everything we're doing is being made by a carbonyl, and then you would just take a water to take that proton off. But what are you really responsible for? You're really responsible for the forward reaction, because we make imines, okay? So I think I've gone over a lot of the material. You've got lots of stuff to work with, okay? I know you feel like you're in a new world, because I do things kind of differently. But really, if you go over your notes very carefully, if you go over the textbook chapters that we're in now, I believe we're in chapter 17, if you go over those flashcards, if you're a real sapling person, you do a bunch of sapling, I just don't see how you cannot be prepared for this, but really use your notes as your basis, because that's the material I covered. You know, you have to cover the material that I covered. You have videos, you have so much stuff to work with, honestly. There's so much stuff out there that you've been given about the Diels-Alder. You must know the Diels-Alder. I expect you to know the Diels-Alder. But do the Diels-Alder in a pragmatic way. Don't do it in a really like highfalutin 3D way. Be pragmatic about the Diels-Alder. Do 1, 2, 3, 4, 5, 6. Put the substituents on flat. Do the stereochemistry on each piece. Then do exo-endo, which is how the stereochemistry of each piece relates to each other piece. Remember when you don't have exo-endo. This is important, right? When do you not have exo-endo? You don't have exo-endo when? It's the 5 rules like baseball. 1. When you have a transdiene file, a transdienophile. You don't have it when you have a ZE diene. You don't have it when there's no substituents on the diene. You don't have it when there are no substituents on the dienophile. And last but not least, you do not have it when the dienophile is a triple bond. Okay? Those are the 5 times you don't have exo-endo. Stereochemistry. If you make something chiral, draw it's an enantiomer, okay, with Diels-Alder. If you start, we talked a lot about this in class, with a pre-existing asymmetric carbon, that center will be fixed in the product. That means the products no longer have enantiomeric relationships and diastereomeric relationships. So if you have a pre-existing center, you're going to get a preferred state of attack, and at most, you're going to get diastereomers. Frequently, you only get one product, as we showed in lab with alpha-philandrine. Okay, so I hope this helps. Thank you. Bye.